Good morning or good afternoon, everyone. Thank you very much, Keisha, for the introduction. Thanks, everyone, for joining us today. Again, the session is how wind turbine owners can use artificial intelligence to reduce maintenance costs and increase energy production. Keisha, could you make me the leader so I can start going through the slides? Thank you very much. So, for introduction, wind turbine operators are using AI in many ways. And one thing that's important to note is AI is not something that's going to happen in the future. It's happening today. I mean, yes, it's going to continue to get more powerful. There'll be more and more use cases, but this is something that your peers in Ensemble Energy, we're using artificial intelligence every day. We're applying it to wind turbine operations. Some of the things that we're doing include we prevent expensive failures. We can predict failures months in advance, which reduces downtime and also optimizes logistics costs. We can identify underperforming turbines very quickly and address that, so we can help improve turbine performance. And then we can also reduce downtime. In the webinar today, we're going to explain how this is being done. We're going to share actual use cases, and then we'll share some best practices for implementing AI at your projects. So your presenters today, this is Rob Budney speaking. I'm a co-founder of Ensemble Energy. I'm a Chief Reliability Officer. My background is I'm a reliability expert. I've been working in industry for 20 years. 15 of that is in wind. One of the things that I do is I teach the AGMA Gear and Bearing Failure Seminar. That's a 3-day-long seminar that's put on twice a year. Prior to starting Ensemble Energy, I worked at a wind turbine OEM for 8 years. I also founded and led a wind energy consultancy prior to Ensemble Energy. So also on the call with us today is Dr. Sandeep Gupta. Sandeep is the CEO and also a co-founder of Ensemble Energy. Sandeep is an energy systems expert. He's got 15 years of experience in wind. Sandeep is a leading expert on wind turbine design, controls, and optimization. I know this because I've worked personally with Sandeep for all 15 of those years. Prior to Ensemble, Sandeep spent 4 years in graduate school doing research on the wind industry. He spent 7 years at a wind turbine OEM, and he also spent 4 years leading a wind energy consultancy. So both Sandeep and I have a lot of relevant wind turbine experience. Just a little bit of information about Ensemble Energy. So Sandeep and I founded the company in 2017. The motivation to start the company was an opportunity. We saw an opportunity to apply artificial intelligence to data in a way that significantly reduced the cost of clean energy. And clean energy is our passion, and so that's what motivated the company to be founded. Our team is comprised of both top data scientists and also clean energy engineers. So it's our belief that domain expertise is required to achieve the full potential of the AI methods. So we think that the domain expertise is just as important as the data science expertise. We don't think that you can extract all of the information out of the data if you don't have an expert understanding of the physics behind the data. So Ensemble is currently working with 5 leading wind operators on a broad fleet, many turbine types, and helping with many different types of operational issues. We are 100% focused on low carbon energy sources. So the industries that we work in wind, we work in solar, and we work in natural gas. The theme here is all low carbon energy. So what are AI and machine learning, or what's artificial intelligence and machine learning? So artificial intelligence is a science of training machines to perform human-like tasks. You might think of a self-driving car or a machine that can play a game like Go or chess or Jeopardy. These are examples of artificial intelligence. So machine learning is a subset of AI, and it consists of algorithms that can learn from past experiences without being explicitly programmed to do so. Machine learning requires 3 discrete elements. First of all, it requires learning algorithms. These have been around since the 70s. It requires meaningful data for analysis. And the last piece is It requires extremely powerful computing resources. So machine learning, while technically possible back as far back as the 70s, it was possible, but it wasn't practical or it wasn't feasible because the computational resources didn't exist. With the advent of extremely powerful and low-cost cloud computing, that last element was in place. So if you're wondering why you're seeing this explosion of machine learning and artificial intelligence now, it's because that last piece, that cloud computing, is now available. So the process of developing a machine learning model, it's an iterative process. So the first step is to ask a question. The next step is to collect the data that's relevant to the question. You'll use that data to train your algorithm. Then you'll try it out. You see how it works, and then you'll collect that. You'll collect that feedback. You'll see, where did the algorithm do well, and where did it do poorly, and you'll build that back into the algorithm. So it's an iterative process. It's a truism that machine learning will only get better over time as the algorithms are exposed to more and more data, and as they receive more and more feedback. The accuracy only continues to improve. Let's talk now about some categories of machine learning problems. So the first category would be a classification problem. So what you're doing in a classification problem is you're predicting or you're classifying from a discrete set of labels. To make this concrete for those of us in the wind industry, an example would be identifying a pitch bearing as failed or healthy. That's an example of a classification problem. There are also regression problems. And in regression, what you do is you predict a numerical variable. So for a wind turbine example, an example would be, given all of the relevant operating conditions, how much power should a given turbine be producing? That's an example of a regression problem. And then finally, we have clustering. So what you do with clustering is you're grouping together by attribute similarity. So for a wind turbine example, we might be able to group turbines together with similar power production and do this automatically, not based on any predetermined rules. So what are the data sources that are used for machine learning models in the wind industry? Well, one is 10-minute SCADA data. There's a tremendous amount of information embedded in this 10-minute SCADA data, so that can be used in many different, for many different components. Another source would be higher speed data, and then that could be higher speed SCADA data, condition monitoring data, oil particle. All these are examples of some higher speed data that can be used as well. It's also important to have the fault log and a description of the faults. That's important information for the machine learning model. Part failure information, and by this I mean specifically what the failure mode of the components was. That's important for the data science team to know something about not just the fact that a component failed, but information about the mode of failure. You need to know which parts were used and when. Maintenance information is also an extremely important input into machine learning models. Just to give a particular example, on a main bearing, it's important to know when the main bearing was lubricated, how much lubricant was added, and it might even be important to know what the formulation of the lubricant is. That's a specific example, but generally speaking, maintenance information, all maintenance activities, it's important to build those into the machine learning models. It's also important to know when the turbine has had a firmware update. When the turbine changes behavior, it's important to know, was that an expected change of behavior or was it unexpected? So by having information about the firmware updates and the nature of those updates, we can not falsely categorize a change in behavior as an anomaly. We can know that that was an expected change in behavior. And then finally, a project wind and sighting report. That can include some very valuable information which can be very useful in generating the machine learning models. So I mentioned at the start of the call that, Ensemble, we believe that the domain expertise is just as important as the data expertise. And I want to give you an overview of our flow. So we start here with the data, and this is what all machine learning companies or all data science companies will do. They'll start with the data. from the data, they'll sort of extract some metadata from that. So they will do things like calculate moving averages, calculate derivatives. So they will, use the data to create features. They will put both the data and the features into the machine learning model. Well, Ensemble does each of these steps, but additionally, we bring the physics into the models as well, too. And the physics can be in many different domains, aerodynamics, lubrication. We use our domain expertise and our analysis tools. For example, we can build models of the thrust load on the rotor. We can build models of a main bearing, and we know when that downwind row is taking all of the load, for example. So we use our physics domain expertise and our analysis tools to create physical features, and we add those to the data features. So we actually have a much richer set of information than, we don't just have the SCADA tags. We have tags that we create ourselves. This is an example of an advantage that is gained by having the domain expertise. When we bring together both the data and the physics into the machine learning models, that allows us to be very accurate with our predictions. And what it also allows us to do is to help our customers understand, what's the most effective action they can take to address the issues that we surface. So we call that a prescriptive action. So it's not just green, yellow, red. If we give the customer an indication that there's a problem, we also help them understand, what steps they should take to correct the problem. So when we first started the company and we sat down, we asked ourselves, what are the features of an ideal predictive maintenance tool? And some of the things that we came up with were, we wanted the ability to identify an issue before any damage occurred. We wanted to provide customers prescriptive actions, steps that they can take to correct the issues that were identified. We wanted any issues that were identified to be explainable and based on physics. And we wanted to be able to provide customers insights into which of their maintenance actions are effective, which maintenance actions are helping, and which maintenance actions are not. And then finally, we wanted to close that loop. As inspections and as maintenance actions are taken, we wanted that learning and that observation to be built back into the machine learning model. As I said, the algorithms get better and better as they get the feedback. So we needed our platform to have the ability to collect the feedback. So we have developed our predictive analytics solution as a software as a service. We call it the Energy.ml platform. Here's just a couple of screenshots of the platform. Now I'd like to start moving into actual case studies where Ensemble Energy has used artificial intelligence to help wind turbine operators. So we had a customer approach us, and they said, we think we've got a lot of yaw misalignment at one of our sites, and it's pretty laborious to have our technicians, climb all these turbines. Can you guys use your machine learning to help us identify which of these turbines are suffering from yaw misalignment? And we said, yes, absolutely, we can do that. What we did was we started with physics models. Again, the thesis of Ensemble Energy is that the domain expertise, understanding the physics, is just as important as the data science. So we started with our customer. We took 2 years worth of SCADA data. And first we started with physics models. We didn't start with machine learning models, but we started with physics models. We applied the physics models to the SCADA data, and we identified which turbines at the project actually had yaw misalignment. So armed with this information, we were then able to build in machine learning what's called a supervised learning model. So we knew which turbines were misaligned. We used that information to train our machine learning models. We were able to do that in an automated fashion. We were able to detect yaw error with the machine learning models using as little as 2 months worth of data. So here's an example. Here's a power curve both before and after the yaw misalignment was corrected. One of the things that we're looking at whenever we create a machine learning model, we want that model to be as accurate as possible. So you're always trying to maximize your true positives while minimizing false positives and false negatives. But one of the ways that you can evaluate that is looking at what's called the precision recall curve. And you can tune the model to get really that optimum balance between trying to get as many true positives as possible and minimizing the false negatives and the false positives. Here's another example of a main bearing case study. I mean, as many of you know, main bearing reliability has been a big problem in the wind industry. Mostly affects what's called a three-point mount drivetrain. Before coming to Ensemble, or before co-founding Ensemble, in my previous consultancy, RBB Engineering, this is one of the things that I did on a daily basis, which was tearing down main bearings and doing root cause analyses on the failure. So it's something that we know quite a bit about. We have developed a methodology where we're able to detect anomalous conditions in the main bearing before serious damage has developed. By doing so, we've been able to help a customer implement a maintenance action which prevented a main bearing failure, resulting in a cost savings of about $250,000. So here's an example. This comes from a tear down that I did. This is actually early on in the tear down process, but it became immediately apparent that the bearing did not have a sufficient amount of grease. And the end result of that lack of lubricant was the development of spalls in the outer ring of the bearing. Now, what people are typically doing to detect main bearing failures is they're using a vibration-based CMS. That can work very well. So the vibration-based approach, you can be notified of a bearing failure, 6 months in advance, perhaps even longer. But the shortcoming with the vibration-based CMS approach is that the vibration requires a spall to be present. So that spall or that pit causes a vibration when a roller rolls over it. That's actually what's being picked up by the vibration-based CMS. So by the time you have a spall, that bearing is seriously damaged and the bearing is going to fail. The approach that Ensemble takes is we're actually looking for issues that are the precursor to the spall developing. So we can notify our customers that there's a problem with the bearing, often with the lubrication system, and they can go in and they can correct that before the spall develops. So we're able to not just detect failures or predict failures, we're able to help customers prevent failures, in this case, a $250,000 failure. I'd like to also talk about now a pitch bearing case study. Similar to main bearings, pitch bearings failures have also been a very serious problem on some wind turbine models. Several failure modes exist, each of which require a different machine learning model to detect. So because the failure modes are quite different, naturally the machine learning model that's required is also different. So here's an example of an outer ring crack failure mode. This is quite a serious failure mode. In some cases, this can lead to the liberation of a blade. So this causes a safety issue, can destroy a turbine as well too. So it's a very serious issue. Here's another example. This is a piece of a broken cage. So there are some turbines which have seen very high rates of cage failures. And then this example here is showing a spallation on the ball path of the pitch bearing. So this is kind of more of a typical wear out failure mode. So the outer ring cracks, they typically they can start occurring from around year 2 on. The cage failure modes, these can happen in a matter of months. The ball path spall or the wear out failure modes, they would typically occur, beyond year 10. So you can look at these failure modes. You can see that the physics of the failure is all quite different. The root cause is different. The symptoms are different. The progression is different. So again, quite naturally, since these failure modes are so different, a different machine learning model is required to accurately diagnose each of these failure modes. And again, this is one of the advantages of having this domain expertise. We can dial in the failure modes for the particular failures that we're seeing. We're able to accurately predict these bearing failures months in advance. It really depends on the failure mode, but a minimum of 3 months in advance, and some of the other failure modes we can predict 6 months in advance. By predicting the failure up to 6 months in advance, we're able to reduce the downtime and also minimize the logistics costs. So no one keeps pitch bearings in inventory, and it could be a long lead part. So by getting a 6-month notification that you have a failure, you can put the excuse me, I'm going to get a glass of water here. You can get your pitch bearing on order, so minimize that downtime. You can also schedule the replacement in a time that's convenient. And then perhaps the most important benefit is if you've got more than one failing pitch bearing, you can get them all at the same time with one crane call out, not having multiple crane call outs. So these are all the benefits that will derive from having a notification of up to 6 months in advance that you have failing pitch bearings. Next, I'd like to move on to a generator bearing case study. So again, generator bearings will often experience several different failure modes. What we've seen is lack of lubrication, we've seen contaminated lubricant, we've seen electrical discharge. All these can be root cause factors behind many generator bearing failures. So here's an example. This particular bearing failed due to contamination of the grease in the bearing. And here's an example of a bearing that failed due to electric discharge damage. We're very successful in predicting the generator bearing failures. We can usually do that weeks in advance. So one of the things that affects our prediction horizon, how far in advance we can actually predict the failure, is how quickly the failure progresses. Now, in the case of the generator bearings, the bearing, it's a high-speed bearing. So damage in the bearing would tend to progress very quickly. In the case of a main bearing or a pitch bearing, these are the bearings move much more slowly. So therefore, the damage develops more slowly. You can have a longer horizon. So on the main bearings, we can predict that many months in advance. Pitch bearings also, we can predict those failures 6 months in advance. In the case of the generator bearings, it's more like a few weeks in advance in terms of the prediction horizon. This is actually quite an interesting study. This is still ongoing. We're not quite finished with it, but we wanted to share the details because we found it was so interesting. So one of our customers, a large number of their turbines at a particular farm, their turbines are faulting due to an inverter over temperature. And when they fault, the turbine will usually be down for about 2 hours before they can bring the turbine back online. So the customer is working with their OEM. They were actually working on the hardware change required to improve. The hardware change is intended to improve the cooling system of the inverter and prevent these. However, there's a long lead time on the implementation, and there's some costs associated with this as well. So our customer came to us and said, hey, can you guys use machine learning to help us out with this? And we said, absolutely. So what we did, we took the data, we built a machine learning model of the inverter temperatures, and we did some forecasting. So we said, okay, this is what we think the temperature is going to be 60 minutes in advance. So here's an example of our predicted temperature. So we predicted this an hour ahead in orange, and then the actual temperature in blue. So you can see that we're able to, with very high precision, predict what the temperatures are going to be. And we're working with our customers to implement an optimal derating strategy. So rather than just running the turbine and waiting for the turbine to fault, and then the turbine being offline for 2 hours and missing all of that availability, we're working with them to develop a way to slightly derate the turbine, keep that temperature below that threshold, keep that turbine online, minimize downtime, and minimize lost energy. We're still in the implementation phase, But we thought this was interesting enough that we wanted to share this with the audience. So to summarize the discussion so far, AI for wind turbine operations is not just the future. I mean, it's the present. It's being used today. So what AI does, it allows wind turbine operators to move from a reactive mode or even a proactive mode to predictive maintenance practices. There's been a lot of sort of headlines about, AI is going to replace us all, and we certainly don't feel like that. We do not feel that AI is a substitute for skilled human operators. There is no substitute for skilled human operators. But what we see is that many of the customers that we work with, they have one engineer or analyst per gigawatt of installed capacity. So people are spread incredibly thin. What these people need, they need tools to help them distinguish between signal and noise. And we think AI is just an excellent tool for doing that. It's not intended to substitute for skilled human operators. It's intended to help increase their efficiency and their effectiveness. So some of the major benefits from AI include failure prevention, failure prediction, performance improvement, and also downtime reduction. So now I'd like to start talking about what are some of the best practices for implementing AI. These are mostly focused on data. So one of the things that we would definitely recommend is that you collect and store as many SCADA tags as possible. We see lots of owners who don't collect all of the tags that are available to them. They want to keep below tag limits, which helps save some expense. But what we find is that the incremental cost of storing additional tags is very low, and that value can be very high. So we would recommend that turbine owners store as many data tags as possible. And, if you haven't done that up till now, I mean, that's okay, but our recommendation is to start just as soon as you possibly can. Another thing that we recommend is that for the 10-minute SCADA data, that the statistics are stored. So, we recommend that the mean value be stored along with the maximum, min, and the standard deviation. That's actually a rich set of statistics. And if you have all those parameters, min, max, standard deviation, and mean value, there's a tremendous amount of information there that can be used on many, many different components. What we've seen in some cases is some owners would just have the mean value, and there's really not very much information there, and there's not a whole lot that can be done just with a 10-minute mean SCADA data. Another suggestion that we have for owners that want to implement AI is to digitize their maintenance records or use a CMMS. And I mentioned earlier in the presentation about all of the sources of information for the machine learning models. An important source of information is the maintenance records. And our experience is that, the more that customers have digitized their maintenance records, the better the records they are, and the easier it is to incorporate that information into the artificial intelligence models. We also suggest that component failure modes be documented. Again, it's not only important to know that a failure occurred, it's important to know what the failure mode was. People often talk about a wind turbine gearbox failure. Well, there are dozens of components in a wind turbine gearbox that can fail, and they can fail in several ways. So it's very important for the person who's building the machine learning models to understand, specifically what the component was that failed and how it failed. That helps to build, the optimal predictive analytics for that component. Okay, at this time, we're going to take questions and answers. So, Sandeep, if you're going to join me here.
Yeah, thank you, Rob.
Okay, great.
So we are open for questions. There are a couple of questions already in there. We can start with one. So Jeff asks, what makes machine learning better than other approaches such as cognitive computing or genetic algorithms? one of the challenges, and I think this is kind of a issue with kind of names, right, and what people use. But cognitive computing, let me take that first. Cognitive computing really is a term that essentially represents, artificial intelligence and cognitive computing could be thought of the same thing. It essentially specifically talks about, mimicking how human brain works. And so that encompasses usually machine learning methods, natural language processing, vision, and so on. So when we talk about AI, and again, in the case studies, we talked about, essentially machine learning methods that have been used, some image processing methods that could be used, NLP, that is potentially a future use case. Once you have CMMS data, if you are now able to, include voice in there, right? Maybe that's something that technicians then don't have to now, take notes, and that helps, with this process. So again, cognitive computing is a little bit broader. Genetic algorithms, on the other hand, are different. They essentially are kind of more like optimization techniques. So machine learning is about finding patterns, and that's an important piece. We are looking to find patterns based on previous history of data. So hope that answers Jeff's question.
Yeah, thank you very much. Let me take the next question, Sandeep. So, or did you have another one that you wanted?
No, I just wanted to, so the next question was, and I think a couple of people asked the question, the main bearing problems, what do you monitor that is precursor to failure? And I think that's a question, excellent question, Rob, if you want to take that.
Actually, I prefer that you take that one, Sandeep. So,
no worries. It's a very good question, and a lot of operators that we work with, their analysts have come up with trending methods, right? So you look at a trend. Most commonly, people would use mean bearing temperature if it is available. For looking at trends, and the temperature starts to increase than expected, then you have a problem. Well, that method works, usually does require, again, the damage to start building up where temperature has now deviated more than what you kind of, would want. What we do differently, what predictive analytics is about looking from the past behaviors and seeing the patterns, and that kind of fits in the previous question, detecting the pattern. You are looking to detect pattern in, maybe it's the main bearing temperature, maybe it's number of falls, maybe it's the power production, that the machine learning algorithms learn happened before the previous failure. So for this specifically, the machine learning also can be classified in kind of traditional machine learning and then deep learning. So this is where some of the deep learning methods are used to essentially figure out the days, hours, months, depending on the failure mode that you're looking at, what is the pattern that was developed before the failures, the historical failures. And that is what model learns and starts to essentially give you an indication of a probability of that pattern matching happening, and then alerts the user to say, hey, we have an early onset of that potential pattern that started to show before all these failures, and you can go and do the inspection to find out what's going on.
Thank you, Sandeep. Let me let you off the hook here, and let me take a couple. So there's a question about have you observed any strong correlations with the environment, driving some of the component issues? And the answer is absolutely yes. So main bearing issues, heavily driven by turbulence intensity and wind speed. Similarly for pitch bearings. So I wouldn't say that every problem has a strong environmental influence, but many of them do have a strong environmental influence. It's actually one of the things too that we can do with the machine learning is we're able to identify which parameters are, we can kind of put them in rank order, which parameters have the largest effect on each failure mode. There's another question, Sandeep, which I can take, which is how much historical data do you need to build a model? That's also a really good question. What we like as a minimum, is 24 months of data. Kind of related to the last question, to what extent, do the site conditions, affect things. So, if a site has a lot of seasonality to it, which most sites do, we want at least, 2 years of those seasons to really be able to get all those seasonal effects. I mean, in a pinch, we can use 18 months or even 12 months, but what we really like and what works best is we have at least 24 months worth of data. Sandeep, do you want to take one?
Yeah, we have another question, and that's actually a very good question from how do you initiate an AI solution for a potential customer who doesn't have the internal expertise to even get started? And it's expanding on that, in other words, how do you break down the wall for those who are overwhelmed with the digital side of their business? It's a very, very good question, and I think it's not uncommon to have that experience. Operators who are trying to find various methods to create value, especially in O&M, as digitization becomes a buzzword. People are starting to think, hey, how do we get started? And our approach has been that we work with our customers to, again, ask a question. What are your biggest problems that you are dealing with? Let's start with that, right? You want to start on a pilot, and you want to start with a small, defined problem with a clear outcome. And once you have that, finding data in an organization which has not been thinking digitally, if you will, in the past, it can take some time. But, data is there. Industrial IoT systems, our systems, wind energy especially has, benefited from SCADA and the data historians that we have. So there is a lot of good data available. But again, the thing is, if you try to take something which is too big, then it becomes overwhelming. So start small, start with a defined problem, help the organization see the value. If you're responsible for that digital digitization or predictive maintenance using AI, work with companies. I mean, there are other companies. We would be happy to talk to you if that's of interest to you.
Yeah, could I just add a little bit to that, Sandeep? I certainly agree with everything that you said. And then, like Sandeep said, we're not the only company that is doing this. So it is an excellent question because this is really a brand new industry. So there's not really so much of a template for how to do this. I've mentioned several times so far the advantages of the domain expertise. Sandeep and I have been in this business for 15 years. So when we go to a customer and we start looking at their SCADA data, it's not the first time we've looked at SCADA data. We've been looking at it for 15 years. So we understand how the data is structured. We understand what it means. We understand how it's stored, where it's stored, the process of getting it out. So having that wind turbine background, having worked at an OEM, having worked with many operators, we're able to help them figure out that roadmap for how they can start achieving the benefits of AI.
Thanks for that, Rob.
Yeah.
I think there's a couple of questions. I think similar questions essentially is how can these methods help analysts prioritize numerous alarms from now multiple input sources, right? And similarly, right, if one engineer is overwhelmed, then how can the methodology help prioritize daily workloads? Rob, do you want to take that?
Yeah, I'll take a crack at it, and then maybe you can just add on to that as well. So, again, what we've tried to do with our tool, when we started the company, really one of the beauties of starting a company is, you have a blank slate. You don't already have a product, and it can be difficult to sort of change the direction of an existing product. So when you're starting with a blank slate, that's a beautiful thing. So, we designed our tool to be, very intuitive. And, we've got some interfaces where we have one of our interfaces is in one screen, a wind turbine technician, a site supervisor, an asset manager can look at a matrix of all of the components, at all of the turbines, all of the components that are being monitored and what the health status is. So that's really a great source of information just in one screen in terms of what the priorities should be for that maintenance actions on that site.
Yeah, just adding to that. Just adding to that. I think this is again designed. I think where you want to bring to the surface the most important issues that are needed attention right away, right? So having multiple sources, say if you have a CMS system which is sending you email alerts, say something's going on, having some kind of alarms, right, OEM alarms now you have to have, and then you have Ensemble, say another platform, let's say you have to do that. Our goal has been to try to integrate some of these alarms that are coming from multiple sources and helping analysts and technicians, site supervisors, fleet managers, as Rob said, to find what are the most important issues based on, again, this predictive analytics and building the confidence during the pilot projects that the nuisance alerts are not there. And again, that is something which is actually an important question, and for folks who again are considering this, it's an important thing to understand that false positives are going to be there. There is no 100% accurate solution, predictive solution. If somebody's claiming that, that's okay. They could have it, but that does also mean that they could have false negatives. Now, a question you have to ask, is a false positive more costly or a false negative, and what is the ratio between that? And that will help you understand and come up with what is the optimal number, and that's the discussion we have with customers. So again, having too many notifications can be nuisance, but having too low notifications can also mean that you're missing out on some of the predictive notifications.
Yeah. There's one I'd like to take, Sandeep, which is,
sure.
Do I need any additional sensors for my turbines to use machine learning, or are the sensors I already have sufficient? So our answer is, when you start working with Ensemble, we're not asking you to install any additional sensors. We work with all of the existing sensors that you have. So you don't need to add a single sensor to your turbine to benefit from machine learning. So most turbines are going to have anywhere from 200 to 300 signals already. So there's already a tremendous amount of information. There's already a tremendous amount of sensors. Having said that, we think that there are cases where it would make sense to add an additional sensor. Thermocouples or RTDs are very expensive. In some cases, in some turbines, there's not a thermocouple where you'd want there to be one. We think you can make a business case in some cases, for example, to do that, but it's not necessary. And then, also just sort of related to that question, we don't see ourselves as being in competition with CMS, or we don't see ourselves as being in competition with any other sensor. What we do, the more data we have, the better. But we love CMS systems. CMS systems work great. They add a lot of value. We can incorporate that into our systems. So it's not an either or. It's not a competition. But we think that AI and CMS can be very complementary. I'm going to pick another question, Sandeep.
Yeah, I think I'm just kind of trying to see if we can couple different questions. Another question is, how are we able to get proprietary data from other systems to kind of use in our models? The answer is we don't use proprietary data. The data belongs to the customer. So as a customer, they have access to, the data that they're getting. It's data, CMS data, and so on. So that data belongs to the customer, and we are able to use that data because customers have. So that is why, again, it's important to make sure that as an owner-operator, that you build data systems that allow you to store historical data. We talk about SCADA data. As the storage becomes cheaper, cloud is becoming more and more accessible. PI System, for example, has just announced, where you could directly transfer data over to cloud, which, again, you can start saving not even just the 10-minute statistics, but you can also potentially save 2-second data or so on if it is available. Currently, we see many customers don't save the high-speed data or save it for only a few months and not historically. So again, it is helpful as we go to this new data age in the cloud that, we start doing that.
Sandeep, there's a question from a former colleague of ours and a good friend of ours. Question on the IEC 61400 and the use of AI. The design standard supports use of a lower material safety margin if a periodic inspection program can detect crack development on some non-fail-safe structural equipment. Do you see AI and SCADA being used by OEMs to facilitate lower safety margins on these structural materials? I definitely see AI being used to facilitate unnecessary safety margins on components that don't have sort of structural consequence. I'm not so sure about things that have a structural consequence. I mean, I'm just trying to think about the question, and I think AI is all about. I mean, to me, it's all about improving efficiency, and there's so many different ways that you can improve efficiency. And I think one of the ways to do that is reducing margin if it's real margin. I mean, if it's not real margin and reducing it, then that's not increasing efficiency. But if you're actually putting in more design margin than you really need, and if you have some way of verifying that, then by reducing that margin, you are increasing efficiency. And I could see how AI can be used for that. For structural issues, I'm not so sure about that in particular, though. If you have any thoughts on that, Sandeep.
I think just in line with that, I think this is something that is likely the future that AI, which becomes a diagnostic tool, right? Well, what is a periodic inspection? It says, hey, you can go every 3 months, inspect that, and you can use a lower margin because you are doing this inspection. Now you have almost a continuous inspection. So, theoretically, I can see that. It will take time, especially certification agencies. They want to see the proof. They want to see the reliability of these methods and accuracy. But no doubt, I think that will help reduce some of the unnecessary margins. That introduces another question. Is then you have to, then the data that gets used in some of these methods needs to now become more reliable. And so that there could be, the development has to happen on that side to make sure the data transfer, the data loss, the percentage of data that's available, that there are some standards set on that. So it'll be a welcome thing. Again, we want to remove inefficiencies where we can, but add material where we need to. And I think there was a question actually somewhere in the middle is, some of the environmental correlation to failures, does that imply that the process, site suitability process, wind and siting process, is that inadequate? And I think the answer, as a former site suitability engineer myself, is yes, and it's not so much that, folks are not trying. The methods have been constantly improving. But one of the challenges has been is that the new conditions where turbines output, people are, haven't seen that in the past, or the new components that are being designed, the bigger components, that the same component in a different condition worked, and now in these new conditions it has failed. So yeah, methods are evolving. Similarly, you've got to have the AI methods to start helping you with on the wind resource and siting side, as well as periodic inspection, or continuous inspection, replacing periodic inspection with this continuous inspection.
So, Sandeep, what that made me think about is, this case study where we showed the yaw misalignment. So, I mean, the question was, how well does sort of the site suitability work? Are the methods appropriate? I mean, I'm paraphrasing. And so, there are certain assumptions made, with respect to the amount of yaw misalignment that a turbine sees. If the turbine sees more yaw misalignment, and not only does it have an impact on the amount of energy produced, but it has impacts on the loads as well, too. So here's an example, where we're using AI detecting yaw misalignment, and having it corrected. So, that makes the actual operating conditions, more in line with what the assumed operating conditions were, what the design operating conditions were.
Yeah, no, definitely.
Yeah.
We
should probably make that the last question, or you have one more that you wanted to do?
No, I think that's, there was a question which is similar to kind of maybe the past, is AI to reduce redundant work as those things that have cost associated, for example, for bolt torquing, etc. And I think the answer to that is it can be used, but it will need to have some of the data required to facilitate those problems. And currently I think that data may not exist, either the maintenance data, historical data of, okay, where, say bolt torquing, etc., led to some problems. And so again, right, we want to go from a periodic maintenance to preventive maintenance. And so the kind of problems in this question was referring to, they can be solved by preventive maintenance, reducing the need to go and do it every 3 months or 6 months. But again, requires that data collection and making sure that you have the relevant information to build those models.
Thank you very much, Sandeep. And so thanks, everyone, for attending. Thank you very much for the questions. The questions were great. I really enjoyed that. If you'd like to learn more, if you'd like to see a demo of our platform, or if you have any questions, you want to follow up with the discussion, please contact me directly. So my email address is there, rbudney@ensembleenergy.com. There's my telephone number listed as well, too. Love to talk to you about the today's webinar and any questions you have. You can also learn more by going to our website, ensemble.energy. And then just one final slide, one final topic. We wanted to mention that the AWEA OMS conference is coming up quickly. The call for proposals is going to come next week. I know Sandeep and I are working on ours. And this is really our favorite event of the year. It's always really great speakers. It's always really well attended. It's in a fantastic location. So we're exhibiting next year. We hope that you will come to the OMS conference next year, and that if you do, you'll stop by our booth and you'll say hi. So thanks again, everyone. Really appreciate your time. I'm looking forward to continuing the discussion offline as well.